And hello, welcome everyone to this video. Let's go on. So, the last time we were talking about getting a Nusselt number from the similarity solution. So we had a Nusselt number, local Nusselt number here, 0.332 times square root of the local Reynolds number times Prandtl number to the 1/3. Okay, so this only applies again for situations where you have Prandtl number of 0.5 and above, and the average Nusselt number NUL is over here. Okay, 0.664 square root of the average Reynolds number times Prandtl to the 1/3 using this integration formula. Okay, so if you're wondering where to evaluate Nusselt number, okay, because you know some properties of the fluid will change with temperature, because for example, density will change with temperature, and that will result in natural convection, which we mostly ignore in the forced convection boundary layer analysis. However, the conductivity of the fluid will also change, the heat capacity will change, the viscosity will change. All of these things will affect your Nusselt number one way or another. And since you have your fluid is at different temperatures at different places, what temperature do you then use? Do you use the free stream temperature? Do you use the surface temperature? Do you use somewhere in between? Well, the convention which is being used is that you use the film temperature. Okay, the average film temperature will be just the average of the surface temperature and the free stream temperature. So you just add them together, divide by 2. That's it. Very easy. Okay, so anytime you see any of these formulas, make sure to evaluate everything by the film temperature. Okay, the film temperature. That's very important. Okay, so as I was saying, we want to move on to integral solutions for the thermal boundary layer with constant temperature flat plate, the most easy kind of boundary layer. So we have a integral solution already done up for the momentum boundary layer as follows, and now we need to consider the thermal boundary layer as well. Okay, so what we do, if you recall, okay, I assume you know how this formula is derived. So what we do is, we consider again our control volume, and we kind of do a momentum balance over this control volume. That's how we derive the old momentum equation. Okay, the boundary layer equation, we derive that. But now we have a similar concept. We also have a thermal boundary layer, which may or may not be the same as the momentum boundary layer, depending on the fluid and its Prandtl number. And then we do a control balance over a control volume, and this time we do an energy balance. And we use the first law of thermodynamics. Okay. Thermodynamics. Okay, so first law of thermodynamics will be applied across this control volume. Okay, the other way, of course, is to integrate your boundary layer equations directly, and that I intend to show a bit later if I have the time, but I'll quickly go through the energy balance part first. Okay, of course, keep in mind that your thermal boundary layer and momentum boundary layer will be usually of different thickness in general. Okay, so it's a constant temperature, plate, and T infinity will be out there. Now, how do you do an energy balance over this? Okay, so we start out with the formula of the energy balance. Okay, Q minus W, where W here is work done by the system. If you use the convention Q plus W, where W is the work done on the system, you have Q plus W on the left hand side. So for chemical engineers, we like to do Q plus W a lot more than Q minus W, which is more the convention for mechanical engineers, because shaft work is being taken out of the system very often. Chemical engineering, we don't do that kind of convention. But just note that there are two ways of writing the Q plus W or Q minus W on the left hand side. So the total energy supplied to the system, the heat and the work done, will result in the net enthalpy flowing out of the system, which means you have fluid carrying enthalpy in and fluid carrying enthalpy out. You have the net enthalpy flows, and of course the enthalpy of the system will also change. Okay, enthalpy is a very easy quantity to use because you don't have to consider the flow work. Okay, and we kind of discussed that before in previous videos, so we're not going to do that again. So let's consider the Q minus W term. Okay, W is 0 because in a boundary layer we don't think about any shaft work or anything going on there, so we're not going to care about W. W is assumed as 0. What about heat supplied to the system? In terms of heat supplied to the system, you only see heat being supplied to the system through the downward part. Okay, through the bottom surface. Okay, so you have a heat flux here. Of course, your fluid will conduct. Okay, so this is a boundary layer. Of course, your fluid itself will conduct heat, but we're going to ignore heat conduction by the fluid. We're going to ignore heat conduction by fluid because this is relatively small compared to the advection term. Okay, this heat conduction by the fluid is relatively small compared to, let's say, the advection term. So in terms of this energy balance here, this energy balance over here, where fluid flows in and out and carrying energy, okay, we are going to ignore the heat conduction terms over here for the time being. Okay, of course heat conduction is present when you transport heat from the left boundary and the right boundary, but for the most part we assume this is quite negligible. Okay, so heat is being transported only through the bottom, so the heat flux here will be K partial T partial Y at Y equals 0. Okay, so that's how we do it. And what's the area? Okay, the area here is dA equals to, well, the Z direction, because this is a X direction. We need to think of the Y and Z direction. So we have a dy here, and then of course a LZ, a representative length in the Z direction, which for the most part we just let it cancel out later. So this is what we kind of get. Oh, sorry, this is not QX, this is QY. Oopsie, this is QY. Yeah, this is QY, so this should be a dx, or just put delta x will do. Okay, because this bottom length here is delta x, and we're going to take limits. We're going to take limits to 0 later on. Okay, so yeah, ignore the dy, we just have delta x. So this is how our heat conduction in the wall will go. dA equals LZ delta x. Okay, and of course we ignore conduction within fluid. This is an important assumption to simplify our calculation a lot, very much so. Yeah, we simplify the calculation a lot like that. We also assume no work done, so W equals to 0. Now the thing is, let's consider the enthalpy flows in and out of the system, and we assume steady state, so that the enthalpy change of the system with respect to time, is also 0. Okay, so enthalpy change with respect to time is also 0, so we need to consider the net enthalpy flows in and out. So let's just consider the left hand side first. So I'm going to delete all of this. Let's consider the enthalpy flows towards from the left hand side. So what's the enthalpy flow through the left hand side? So it's actually integral of dH, where H is like the finite enthalpies. Okay, how do I put it? It's the, let's say for an area here, how much enthalpy is flowing through. Okay, a small little area, the enthalpy flow through that area is dH. So you're summing up all the small elements of enthalpy that flowing through this left hand side. So the inflow is as such, because I mean your fluid is flowing this way and bringing enthalpy into the system. Okay, so what is this? This is actually equals to the specific enthalpy, and you have your mass elements. Okay, so you assume that the specific enthalpy doesn't change over here. At here, let's say it's x, here's x plus delta x. So this is all evaluated at x. What is dm? dm is again rho dv, and that is rho u dA. And what is dA over here? Because this is mass flow rate along the x direction. So, and we assume that the y direction and everything doesn't really matter here, because this is actually perpendicular to this is parallel to the y direction. So rho u x. Okay, so this will have to be dy, and you have an lz over here. This is the representative length in the z direction. So we'll have to substitute all of this in. Okay, rho ux h lz dy. Okay, so this will be the flow rate introduced at x, and of course the outflow is just this quantity evaluated at x plus delta x. So this is the outflow through the other side. Okay, rho ux h lz dy. Now you evaluate it at x plus delta x. Alright. So that's the inflow and outflows. So that part is settled here. Rho u h lz dy at x, rho u h lz dy at x plus delta x. Okay. Alright, so of course you integrate from 0 to delta t. The delta t is the thermal boundary layer thickness at the point in x. Now one more thing we'll need to do is actually to include, alright, what is the enthalpy, what's the specific enthalpy here? Okay, so specific enthalpy, I mean the enthalpy that's coming in, okay, is equals to Cp dt. Alright, dH equals to Cp dt, or H equals to Cpt minus T ref. So this is some reference temperature for your enthalpy, but of course you will see later on that all of the reference temperatures cancel out, because for thermodynamic properties we always like to use a reference temperature to measure our enthalpies by, or whatever thermodynamic state properties by. So yeah, I hope you remember your thermodynamics class. I'm not going to go through that. Alright, let's see how much time. Okay, so yeah, an important note, we are neglecting the effect of kinetic energy in our energy balance here, so all of that is kind of just thrown out. Yeah. If you want to include kinetic energy, you will have to add another term in there. So how do we do this? Okay, so H equals to Cp T minus T ref, where T ref is some arbitrary reference temperature. Okay, Cp is this is some arbitrary reference temperature. We'll see that it will cancel out later because we actually take limits and we get derivatives. So we'll do the same for the bottom here, outflow through the right. Okay, now what about the top? Okay, this one will be x plus delta x. So this is the outflow through the right, and let's consider the inflow through the top. Okay, because through the surface at the top. Okay, let's take a look at the top surface. Okay, through the surface at the top, there's also going to be inflow of enthalpy. Okay, so the formula is going to be pretty similar, but this surface is pretty awkwardly angled. It's not a straight 90-degree angle with the two other surfaces on the left and right. It's at a slant angle that's that will kind of match the slope of that boundary layer. Okay, so how do we get the inflow of enthalpy here? So that's a bit more challenging. Okay, but let's simplify some things for ourselves. We note that over here, we zoom in here close to the thermal boundary layer. Okay, so we note the top surface. Okay, let's use a different color. We note the top surface here. Okay, what's the temperature outside the boundary layer? It is T infinity. So you can kind of think of the enthalpy, the specific enthalpy here being Cp T infinity minus T ref. So that simplifies things for us. So once you find the specific enthalpy, you just need to find the mass flow rate through this surface. Okay, so you find the specific enthalpy and the mass flow rate, and then you're pretty much done. But how then do you find the mass flow rate? Okay, the mass flow rate is pretty simple. Okay, you just take the mass flow rate of the right hand side minus the mass flow rate on the left hand side. Okay, because there's no mass flow rate going through the bottom, you can only think of the mass flow rate of the left and of the right. So the difference of those two mass flow rates will be the mass flow rate to the top. Okay, so again, the specific enthalpy here is pretty straightforward because it is at the free stream temperature, which for simplifying cases is for simplified cases in our boundary layer is pretty much constant. But then what's the mass flow rate? Mass flow rate equals to mass flow rate of the right minus mass flow rate of the left. Okay, and what is that? That is actually again, we can integrate rho u, okay, rho u a, or rho u dA, okay, at x minus rho u dA x plus delta x. So that's the mass flow rate. Okay, and this is just mass balance, nothing too fancy there. And then what do? You separate out the dAs. Rho u dA becomes what? So dA is this mass balance is over here. Okay, dA is actually again Lz dy, and you evaluate all these at x minus integral rho u lz dy x plus delta x. Okay, so let's write this down. Okay, inflow through the enthalpy through the top. Okay, specific enthalpy. What is it? H infinity equals to Cp T infinity minus T ref. Very simple there. What's the mass flow rate? So mass flow rate, it's dot m equals to integral 0 to infinity rho u lz dy. So anyway, just some sign convention. This is mass flow rate out. Okay, if you want a mass flow rate into the system, you have to switch around the signs. So if you want a mass flow rate into the system, you have to change the signs here. So it is this minus this. Well, that will be the mass flow rate into the system. So okay, I think I made careless mistake there. M right minus M left is correct. So I should all the minus signs are kind of, you know, topsy-turvy. My bad. It's a careless mistake just now. But yeah, just take note. M right will be this term, x plus delta x here. M left will be the mass flow rates evaluated at x. Okay, so let's do that. Into system will be as such minus okay. So if we want to put this together, we will get the following formula over here. But just to, okay, what you see is this, oh sorry, this is not infinity. It should be at the boundary layer. Thermal boundary layer. At the thermal boundary layer. Okay, so I'm just going to ignore this. And let's put this together. Okay. Not m h infinity equals, okay, so we just substitute in wholesale. So this is the only one at the top that you're going to have to kind of worry about. Okay, so this is one approach of doing it, and okay, we're just going to quickly take limits. So let's substitute. Okay, we'll substitute everything back. Okay. So let's have our Q minus W equation. So I'm going to paste it twice, and some things I'm going to just substitute as 0. So the time aspect is 0. There's no work done by the system. That's one. So what's the heat flux into the system? That will be this term here. Okay. Times the area. So the area is this dA. And what are the net enthalpy flows out? Okay, so net enthalpy flows out. That will be what do you call that? Yeah, so whenever we have an inflow here, we just put a negative sign. Whenever we have an outflow, we have a positive sign. So that's net. Okay, enthalpy. So we consider the top first, the top layer, which is over here. Since that's what we just did, inflow through top. Okay, the inflow through the top is this. Okay, so this will be a negative sign because this is a this is an inflow. Inflows are negative, outflows are positive. So that's one. Next one, it's outflow through the right. Outflow through the right is what? Negative. I mean, outflow is positive. And then there'll be inflow through the left, which is a negative. And then we should be ready to take limits now. And as usual, the equations are so long that they will just run off the page. So let's make life a little easier for our. We need to view it properly. And don't worry about this. I'll be intend to go through it later on. Okay, so this is the equation we have now. And what we want to do now is to just divide throughout. Get rid of the zeros. Okay, divide throughout by delta x and take limit delta x goes to 0, and that's how we get our integral equation. Okay, not that difficult. Okay, we're almost at 30 minutes, but I'll just finish this up and we'll call it a day. Oops, shouldn't be here. It should be here. Okay, so let's substitute. We divide throughout by delta x and we get rid of the zeros. So we get rid of the zeros. Okay, so very easily you should see the what do you call that? You should see the integration coming in. I mean the differentiation part coming in very easily, because when you take limits, you'll see the derivatives come. Okay. Okay, so you can see this part is going to be a derivative, and this this thing t infinity is kind of assume t infinity is constant with x, right? Assume t infinity is constant with x. All right, so we save ourselves some trouble there. Normal like For our flat plate, that will be true. So we put this assumption here, make life easier for ourselves. Okay, so we will get the derivatives. So you see, this one's at x plus delta x, this one's evaluated at x, so this whole integral will be differentiated. Okay, so let's do a partial. Same goes for this part. This whole thing will be a derivative. Of course, because of the derivatives, we can drop out the reference temperatures as well. Because that doesn't it's kind of redundant at this point. So no matter what, you can see that this part will just drop out. Okay. Of course, you bring in your CPT infinity. T infinity into integral. And this heat capacity and everything here, these are all averaged values, so they don't change with x or y. Okay, and now of course I can bring out the awkward looking brackets there. Ah yes, I forgot to take out the delta x on the left hand side. Oh, yeah, you just copy so many equations over. No wonder I was so confused. Okay, that's better. Alright, yes, I think this part needs the delta x to disappear. 1, 2, and 3. Finally, get rid of LZ because this is a 2D problem. Alright, and we are done. Almost done. Okay, let's get rid of LZ. 1, 2, 3. Okay, now we want to tidy up equation. We will get this expression here. Let's see. So there'll be a t minus t infinity, and then we can just condense the whole integral down. Okay, so this will be our equation right here. Okay, so this is our integral equation. Of course, if you notice over here, this delta t doesn't change with y. Okay, rho doesn't change with y, u doesn't change with y. Okay, u does, right? Yeah, but it will kind of be integrated out here. Okay, this whole term here as a whole has no dependence on y, because y is integrated out over here by substituting in. So this whole function here, this integral, this definite integral with respect to y, only depends on x. So we can actually change this partial derivative to a total derivative. So d by dx. Okay. Y is integrated out, so the integral on the right hand side does not depend on y, because when you integrate out this, you replace it with 0 and delta t only depends on x, it does not depend on y. Okay, so that's how we get this equation here. Alright, so with suitable boundary conditions, you should be able to solve this equation, no problem. Okay, so you can bring rho and Cp out, even bring rho Cp out, because and rho Cp here is the volumetric heat capacity. Okay, let's see. Did I copy the right? Oh, shucks. Yeah, I think. Yes, I copied the right equation out. You can bring rho Cp out. Okay, did I yeah. Okay, I was typing it at the wrong place. Sorry. You can bring out rho Cp and you will get here. Because these will be average values at the end of the day. So that will be your form of the boundary layer equations. Now, of course, you bring it to the left hand side, you just have an alpha down there, but I'm not going to do that step. Okay, so usually this is how we do the control volume kind of analysis, and this will be your boundary layer equations. Okay, using von Karman type analysis, very approximate analysis, but it's very intuitive. The other way, of course, is to try, of von Karman's integral approach is to literally integrate this energy equation across the whole y domain, and then you use Leibniz rule and all that. But okay, I will see whether you can talk about that in the next video. For now, thanks for watching. It's a rather long video, I know. Okay, see you.